So we'll go over the series divergence test. So the series divergence test. I'll try to limit my usage of this word, because then my computer will turn on with you know what. So if we take a this, if we have a this, and if this series is the following, we have a sub n, and if this converges, then one thing is for sure: the limit as n approaches to infinity of a sub n is 0. However, it is not the other way around. You cannot say that the limit as n approaches to infinity of a sub n, if this is 0, then the series converges. We cannot make that claim. It isn't. You can't go in the opposite direction. You can only go in this direction. So you can say that if it converges, the limit is absolutely going to be 0. But we can't say if the limit is 0, then it's going to converge. So that's just one thing. And so to show a series diverges, it's enough to show that the limit as n approaches to infinity of a sub n is not equal to 0. Because if the limit is not equal to 0, then we can prove that we can show that this is divergent. So basically this says, so this is what you have. I guess you could say, therefore, if your limit as n approaches to infinity of a sub n, if this is not equal to 0, or if this does not exist, right, dne, then the series n equals 1 to infinity of a sub n diverges. Make sure that you get this, because let's just see. If a series a sub n converges, then for sure your limit is equal to 0. But if your limit is equal to 0, you cannot say that your series converges. So you can't go on the opposite direction. But you can say that to show a series diverges, all you need to do is just show that the limit as n approaches to infinity of a sub n is not equal to 0. If it's not equal to 0, or if it does not exist, you can automatically say that your series diverges. That's the series divergence test. That's why it's called the divergence test, because it helps you prove that something is divergent. Not necessarily convergent though. So that's what it's called. So let me give you an example here. So if we were to say, so this is an example. If you were to say that your series we have going from 1 to infinity, if we have this, and we have, let's say for example, we have 1 divided by x. Does this converge, or not x, sorry, n. 1 divided by n. Does this converge or diverge? According to, well, this is a popular series. This is the harmonic series, in case you don't know. The harmonic, and I'll make a separate video on p-series and harmonic series. It's a pretty big topic, harmonic series. But, and the harmonic series, when you learn it, you'll know that it's divergent. But let's prove that, let's show that using the divergence test. So we can go ahead and take this, which is your a sub n. We can take the limit as n approaches to infinity of 1 over n. This is a very nice limit. This is an easy limit. Your denominator is going larger and getting larger and larger as your numerator stays the same. So this has to approach 0. Since 0 is, of course, 0, we cannot say that it converges because it doesn't go that way. But we cannot say that it diverges because it's not. Well, let me say this again. We cannot say that it diverges because it is, well, of course, it is equal to 0. It's not dne or not equal to 0. So since this is the case, we actually cannot use the divergence test on the harmonic series. This is a bad example that I chose. I shouldn't have chosen this example. But yeah, you cannot use the divergence test on the harmonic series. This means that this doesn't show you that it's convergent. This also doesn't show you that it's divergent. It's just inconclusive. So it's inconclusive. This is not the best example to show out there. Since this is equal to 0, it is inconclusive. We cannot show that this is divergent or convergent. We're using, of course, the divergence test. But there's other ways, and in fact, the way you would determine if it's convergent or divergent in this case would be using the p-series, because your p-series, if you have n raised to the first power, which is what you have here, basically when n equals to, when your power is equal to 1, when your p is equal to 1, you are divergent. And that shows that it's divergent. Or, of course, there's other methods, there's other inequalities that you could show as well, but that's not this video. So, of course, in this case, it's a good example to show that your divergence test is not always going to help you. If it's equal to 0, it's not going to help you. But if we were to show another example, let's just say the series from 1 to infinity of the natural log of n. Now, it can't be from 0 to infinity, because when n equals 0, we have undefined. So this we can start with the divergence test. Limit as n approaches to infinity of the natural log of n. So your n goes, you plug in 1, plug in 2, plug in 3, your n goes on to infinity. This whole thing, as n gets larger and larger, this whole thing is actually just approaching to infinity. Since this is approaching to infinity, this is not equal to 0. Since it's not equal to 0, we actually can say that this diverges. So this is a divergent, so let me write that out, divergent series by the divergence test. So that's just a quick example of the divergence test actually helping you. So oftentimes what you should do is you should always check the divergence test before checking any other tests, because that's sometimes can help you. But sometimes you don't need to write it out. You can just check it in your head and be done with it. That's it.